In this work, we study embodiment scaling laws and learn a single policy that can generalize to diverse embodiments in both simulation and the real world in robot locomotion. Generalization is a grand challenge in robot learning, and scaling laws have been underpinning recent advances in learning policies that can generalize across environments and tasks. Yet, broad generalization along another dimension, robot embodiments, remains a significant challenge. Embodiment-level generalization is critical because it can bridge the embodiment gap caused by many factors, including hardware degradation, design improvements, or deployment of heterogeneous platforms. To achieve this goal, we hypothesize embodiment scaling laws, that training policies on more embodiments leads to better generalization to unseen embodiments. To study this, we use robot locomotion as a testbed and generate a diverse embodiment dataset, Genbot-1K, spanning more than 1,000 humanoids, quadrupeds, and hexapods by varying geometry, topology, and additional joint-level kinematic constraints. We train policies using a single unified model architecture capable of handling diverse observation and action spaces on random subsets of the Genbot-1K dataset. We vary the number of training embodiments and found that the performance on unseen embodiments improves with the number of training embodiments within each morphology class. Further, when we train policies on the combined full embodiment dataset, the resulting policy can much better generalize to new embodiments compared to training on one morphology class. We also compare against collecting more data on a fixed set of 40 embodiments and found that scaling embodiments is much more effective in enabling embodiment-level generalization than scaling data alone. Here are some qualitative results on evaluating the best policy, which was trained on 800 embodiments, on some example training embodiments, and on some unseen embodiments. It can be observed that the dataset covers diverse variations across the 3 morphology classes. We deploy the policy directly on unitary goto and vary the joint limit configurations. The policy is able to zero-shot transfers across these embodiments. This policy also transfers to a highly challenging physical platform, humanoid H1, demonstrating strong sim-to-real and cross-embodiment generalization. We create diverse embodiments by varying joint limit configurations on these hardware platforms, and our policy generalizes to these unseen embodiments. Overall, this work shows that through embodiment scaling, we can learn a single policy that can generalize in both simulation and the real world across many different robots. We hope this study of embodiment scaling laws in locomotion inspires further progress in other task domains and contributes to the pursuit of learning broadly generalizable robot policies. Thank you.